Day 3, residuals. Residuals. A residual plot is a scatter plot. That displays the residuals remembering what the residuals are, it's the measured amount minus the expected amount, y minus y hat, or the measured response minus the expected response. On the vertical axis, bless you. Makes sense that it'd be on the vertical axis since they're y's. And the explanatory on the horizontal axis. The explanatory being x. So it's another type of scatter plot. And it's another way that we can decide if we have a linear situation or not. We're going to talk a lot about how to decide if something's linear or approximately linear. We actually hope to see a scattering of the data. It actually reaffirms a linear pattern when you're graphing just the x and y. So a residual plot looks a little different than a regular scatter plot. You have your x and you have your y minus y hat, which is what that would be for your y values. But it always has a horizontal line that's in the graph. You don't have to ask for it, it just makes it. And what you get, or what you want to see is you want to see a scattering of the data, no particular pattern, top and bottom. If the residual plot shows a scatter, then that indicates that the original plot is probably linear. It's the opposite of what you would think you would see. You look for a scatter to see linear. So if you have a residual plot where you don't have a scattering, you actually see some pattern of some sort, let's say something like this perhaps, maybe a kind of a parabolic shape or some sort of pattern in there that you can identify in one way or another, then this would indicate that your data is not linear. So if you see a pattern, linear or or nonlinear. And the pattern could be actually a line, it could be a curve, it could be anything. If you think you can see a pattern in there, we're not linear. All right, the calculator actually stores the residuals in a list. You don't have to calculate each of these residuals. The list is called resid. And to get that list, the first thing you have to do is you have to make your line reg calculation. So to get there, you go second stat, which is your list to access the residuals. After your line reg a plus bx calculation. Alright, so that's a bunch of notes. It doesn't really start to make sense maybe until we actually do it. So let's take the data that I gave you and see if we can't make that work. I'll give everybody a second to kind of get caught up on the notes here so we can play with the calculator. Everybody with me, more or less? Good? Okay, I'm going to zoom in on the calculator a bit here. So we have our data, and again, these are humerus or actually femur and humerus bones of those Archaeopteryx. And to be fair, this is not going to be the best of examples, mainly because there's only 5 points of data here. Okay, so this is more mechanical than it is, hey, there's a great example. All right, but I didn't want to take too much time putting in a big long list of data. So here's what we need to do. We need to run our line reg calculation. So we're going to go to stat, then over to calc, and do the line reg a plus bx. And if you remember, this is a very linear thing. It had a very strong pattern. So L1, L2, that's great. Frequency we leave blank. Store the regression equation. I don't think we need to do that. I just want to make the calculation this time. So you can if you want, but it's not necessary. So we're going to calculate. Now, when we make that calculation, the calculator goes, oh, you need the residual values for that too. Well, let me store that for you. You just have to know where to get it. So r squared and r, we're going to talk about r squared today, but they're both very strong. Okay? So remember, this is a very linear pattern, right? These points almost lined up perfectly. So let's take a quick look at the graph. So L1, let's put in L2, just so we remember. You know, it might be wise to go to y equals and see if there's anything that you need to clear out of there. I think I'd get rid of anything that's there so that you're just getting the scatter plot. So if that's clear, we can go back and hit graph, and you'll probably need to zoom 9 that. So again, there's the data, the x and the y data. But we would like to graph the x and the y minus y hat data, the residual values. So to do that, we can choose our residual values. So there's no
okay,
like...
at this time for our seniors, we will have M and N. Just the two letters, M and N. Thank you.
Just the two. None other than those, just the two. Okay. All right. So if that's you, feel free to go. So to get to the residual list, what we do is we go second stat. You use your lists. And if you look at the bottom, now yours might not be 8. Mine's 8. It can be different, but it's almost always at the bottom. Choose resid. Second stat. Second stat will get you to your lists. So instead of L2, we're going to put the residual values, and we can graph. And you'll have to zoom 9. And there's your residual plot. Now, is there a pattern? I don't know. Probably not. But again, I mentioned that this isn't the world's best example simply because there aren't enough points to define if this is a true scatter or not. But if we were to see a pattern here, definitely like a straight line or something, which we don't really see, then we have some extra indication that we do have a linear pattern. Does that make sense? So it
That is a pattern, isn't it?
is it?
I mean, it kind of looks like a line under the...
It does kind of look like a line, but then when you take into consideration this guy way outside, and the fact that we only have 5 data points, it makes it a difficult one to assess. You'll see some more in your assignment today where I think it'll be a little easier. But again, I didn't want to weigh us down with a whole bunch of data. Okay? All right, now, so we're going to assume that that's a scatter. So we've got a linear pattern. Let's take and start our next bit of notes, and we'll come back to that. So there is a standard deviation for the residuals, and it's a little tricky. We use the letter S. One of the unfortunate things about statistics is sometimes we use the same variable for different things. So we've used S for the standard deviation of you know, a set of data, but now we're also using it for a standard deviation of residuals. I don't know why they do that, but they do. To be fair, I doubt you'll be asked to do this on a test. But I definitely want you to see it at least once. And so the standard deviation is the typical variation of y from y hat. So what that's saying is the typical distance that the measured value is from the predicted value. I'm really struggling with writing today. I don't know why. It's probably because it's almost Friday. All right. And the standard deviation looks like this. So it would be S equals square root the sum of y I minus y hat. I think you'd probably put an I in there. Squared divided by n minus 2. A better way to write that is the square root of the sum of the squared residuals divided by n minus 2. Okay. And this particular calculation would be a bear, because each y and each y is going to have its own y hat value based on the x that it's not quite like x bar where it's the same for everything. So let's see if we can pull that off in the calculator. There's no shortcut for it. But using the lists, we can make it a little easier. Okay? So I'm going to go back to the list and edit. Okay? Now, I'm going to go over to L3. Go up to the top, and I want to put the residual values in for L3. And there's a couple other things I'm going to show you here real quick. So if you go up to the top and then we go second stat and we choose residuals, then it'll show us what those residual values are. Now, there's a property of all residuals. I don't know that this property is important if you're using a calculator, but if you were doing this by hand, this would be something you'd want to check. The sum of the residuals should always be 0. So let's add up our residuals here. So to do that, just to check it, this isn't part of the standard deviation calculation. I'm going to go over to math. So second stat, over to math. I'm going to choose sum. And what do I want the sum of? L3, yeah. Or the residuals, you could say residuals there too.
How'd you get the residuals on that?
Go up to the top, go second stat, and then put in residuals. Yes?
Okay, so putting in the residuals the first time, I did that, but then it freaks out at me.
It freaks out at you. Well, that's not very nice.
So, should I click enter?
Okay, so it didn't let you put the residuals in at all?
Well, it says resid right there, but I don't know if you
Yeah, hit enter. Did it?
No, quit.
Are you at the very top? Yeah, you got to be at the very top. You got to be right on the L3.
Oh, I can't quit it. Oh, got it. Thanks.
You got it? Okay. So this is our sum of the residuals. Are you willing to accept that a decimal point, 11 zeros, and a 1 is an acceptable version of 0? So the reason it's not giving us 0 here is because it's rounding. There's some rounding error in there. So I think we can accept that that's 0. So the sum of the residuals is always 0. It's kind of like the area on top equals the area on the bottom. Yes?
What is that equal?
That 1e to the negative 12. What it?
You take a picture too. Which one do you need?
I don't care. What do we got?
One? I don't know. Both of them.
Both here. You probably want. You don't really want that either, do you?
I don't want any of them.
Yeah. Okay. So what this means, this 1e to the negative 12, is it's 1, and the negative 12 is saying, here, I'm going to move the decimal 12 spaces and put in a whole bunch of zeros. So are you willing to accept that a number like that would be 0? Okay, that's what that is. It's scientific notation. All right? So let's get rid of that. If you have that, delete that. We don't need that. Now, what we do want to do is we want to take and square these residuals. So let's go to L4. Let's go up to the top. And let's square L3. Or you can even put the residuals in and square it. So I'm going to go second L3. And then I'm going to square that. Okay. They all should be positive now that we've got squares. and I want to add those up. So I'm going to do exactly the same thing that we did when we checked to see if there was a 0 there. So I'm going to go down to the bottom. I'm going to go second stat. I want math. I want the sum. And what do I want the sum of? All of the squares. So L4. There's probably a quicker way to do this, but there's not a shortcut way to do it. Okay? All right. So this is the sum of all of the residuals squared. Now, what we need to do is we need to take and divide that by n minus 2. So n being 5, because I've got 5 sets of data here. So minus 2 would be 3. So I'm going to divide that by 3. So I think the best way to do that is I'm just going to use this space below it, and I'm going to go 11.785 divided by 3. And then I need to take the square root of that answer. So in the next box below, I'm going to take the square root of 3.9283. This would be our standard deviation of the residuals. So it's almost 2, right? Almost 2. There's a way to do this in the calculator that will give you the wrong answer, but it's tempting. Let me show that to you as well. Was everybody able to get there or get close, hopefully? Okay. All right. So if you go to your list, second stat, and you go over to math, you'll see, hey, there's standard deviation. Oh, that's cool. Why can't I just take standard deviation of the residuals? I'm going to try that. But I don't get the same answer. The reason is this standard deviation formula is dividing by n minus 1, not n minus 2. That is the whole kicker to that. Otherwise, I think it would work beautifully. So, yeah, that's tempting. It's tempting. It looks like a nice shortcut, but it doesn't really work.
So why is it n minus 1 instead?
Basically, the minus 1 and the minus 2 has to do with sort of margin of error. They want to make sure that your margin of error is such that you're not getting a wrong answer on accident. Does that make sense? So the n minus 2 kind of gives you a bigger margin of error. And we'll learn more about that in future lessons, but yeah, that's like second semester stuff. So the margin of error changes basically with that. Okay? All right. So standard deviation, I doubt you would see a test question on it. You've now seen how it's done. We need to talk about one other big idea, r squared. I've mentioned it, now we need to throw it into our notes. So r squared indicates the strength of a y-hat prediction. And it literally is just the r value squared. There's no secret about it. So your values, your range of values are going to be between 0 and 1. No negatives in this case. So example, let's say I have an r squared value that's 0.6. How we could interpret that is we would say that about 60% of the y-hat predictions would be good. words, 60% of the time, the line of regression is correct. If it was 0.9, then 90% of the time, the y-hat prediction is correct. 20%, 20% of the time. What value, what percent of the time would you be comfortable with saying that, hey, I'm okay here making this prediction? What do you think? 80? Okay. Let me throw it out at you a little bit differently. What if you could predict winning at a game of chance in Vegas, let's say, and at what percent of the time would you be happy with being able to win a game in Vegas and know that you'd come out a winner and beat the house? How much? Thought I heard yes?
85.
Well, that'd be awesome. 80, 85, they'd probably kick you out because they'd go, this guy's too lucky or this girl's too lucky.
50.
More than 50.
65.
No. More than 50.
Really?
Just a shade over 50% of the time. If you can beat the house more than 50% of the time, then you're going to win. You're going to, in the long run, you're going to win. So R squared kind of works the same way. If R squared is 0.5 or better, larger I guess is what I should say, then we can consider it's an indicator that it's an indicator that a pattern is linear. A strong indicator. It's not everything that we want to look at, but it's a big part of it. Because we also have the residual graph to look at as well. What does R have to be for R squared to be greater than 0.5? Well, if I take 0.6 for R and I square that, that's not 0.5. What if I go 0.7 and I square that? That's close. It's got to be more than 0.7. So R has to be greater than plus or minus 0.7 to consider a pattern to be linear. So here's the thing that you want to remember. R squared, 0.5. R more than 0.7. Okay? Better than 0.7. Or less than negative 0.7. Here's a thought for you on this. This is just a quick situation. Let's say our line of regression is a curve. But we're only looking at data that falls, say, between here and here. What's that line going to look like if we zoom in on it that closely? It's going to look straight, right? So these are methods to tell if, in fact, you do have a curve when it may look very straight. Okay? So when you're zooming into a small area, sure, any curve is going to look straight if you're zooming into a small enough area. All right? Okay, I think that's what I want to say. Good job if you followed that.